And we are now recording. Okay, good. Thank you. So we have this is just for, because we're now recording, this is free response, the free response for the progress check, unit 1 from AP Physics CE and M from 2020. We are looking at a length L for two things. We have on the inside a non-conducting cylinder, and we can kind of show that a little bit by like going here and going like that. It kind of goes over there. Okay, that's the cylinder. Yeah, and we have out here a very thin cylindrical shell of radius 4r, which is conducting, and we have on that a charge of -2q, and again the inside charge is +q. There you go. And now we're going to ask some questions about it. They told us that the inside cylinder has a constant charge distribution. So to find the density, all we're going to do is take the total charge, which is Q. It happens to be exactly Q, and divide it by the volume. So basically, this is mostly just a question of being able to figure out the volume of a cylinder. And of course, the volume of a cylinder is just the base times the height. That's it. And we're done. Yep, sure are. That's part A. That would be cool if it was that easy on the actual exam.
Very much so.
I have a feeling it's not going to be. Okay, so let's take a look at part B. Derive an expression for the electric field E of R for the following regions. I'm assuming they're just going to say everywhere. Is that right?
Yeah, they do.
They do. Okay, well, let's just kind of talk about this a little bit. So they don't say that right now, but if you look at this situation, you should be thinking about what's in order to find the electric field. Yannis?
The electric potential?
No. Are you unsure? That's cool. So anytime we have an electric field we're trying to find based on charge being present, you should be thinking of a law named for a famous German mathematician. Gauss's law. So we need to be looking at Gauss's law here in order to do that, okay? And wherever we're going to go, we're going to use a Gaussian surface that we are going to be able to draw in as such. Yeah, okay. So we're going to they're kind of making an assumption here that this thing is actually, that's why that infinitely thing was in there, because we're going to get some edge effects. Do you have an idea what I'm talking about right now? Okay.
Not much.
Okay, so let's take they have a picture on the right, and maybe that'll be a little easier. When we see the picture on the right, you see kind of a situation where you have that inside, that's the non-conducting, and then you have the conducting one around here, right? And you have here negative charge, right? Specifically, and then you have positive charge here. And they're also all through here. Yeah, that makes sense so far?
Mm-hmm.
Okay, so based on that, for example, in between, what's the electric field look like?
0.
Whoa, no, not good. So electric field goes from what kind of charge to what kind of charge?
Positive to negative. So it's
positive
pointing
to negative, okay. Yeah. So it should be pointing in this direction like this, right? And it will look like that. That's cool. And if we use Gauss's law, I don't know if I have enough lines here, but whatever. Gauss's law makes sense of that, because if we did do a Gaussian surface, right, and we could use blue as our color there. So we could have a Gaussian kind of cylinder here at that radius, for example. Okay, and then we could have that thing come out beyond the edge of this thing. So we have this, so there are two views here. There's this thing, the outside cylinder, the very thin one, then there's the inside solid cylinder, and then there's this Gaussian surface in blue. And in our big picture, that would be like kind of like this. Yeah, and then of course it needs to go through here, and inside, yeah, it could keep going like this. And we could, for example, just make it go like really far away in both directions, right? Okay, and at that point we'd be like, oh, okay, we're going to assume the electric field is uniform in here. We could really use that because we're not that good at math, right? So this is going to help us actually be able to deal with that surface integral that's really terrifying us right now. Terrifying to us, not terrifying us. Okay, what else? Okay, does that make sense so far?
Yeah.
Okay, now the thing is though, and here's what we're doing, we're basically ignoring the fact that this is it's not just kind of like a capacitor. Well, it's kind of like a capacitor because it doesn't have two metal surfaces, right? But imagine the inside was metal and the outside was metal, and you had like a positive charge here, negative charge there. Then we have a cylindrical capacitor, and as you know from capacitors is that inside there's relatively uniform field, but on the edges you get edge effects, okay? Because you're going to get basically over here, for example, the positive point is here, this is negative, and the electric field's kind of going to come out and then go hit that edge over there. Does that make sense? And we're going to ignore that. And I think when they wrote the question, they were trying to avoid that. So they were just saying, we're going to take two infinitely long cylinders, and we're just going to look at this aspect of it. And in that aspect, over a length L, we have out here minus 2Q, and inside here we have plus Q. Otherwise, we really can't do the problem. Okay? So let's just rephrase the problem the way I think they're meant to write it, which was we have two infinitely long cylinders. This one is a non-conducting cylinder. This is a conducting shell outside. They're both cylindrical and they're infinitely long, or really long would be kind of the physicist approach to that. And we're just going to look at this aspect of it, and over this length L, our charge on the outside is minus 2Q, and our charge on the inside is Q plus Q, and we don't have to worry about weird field, but instead, we can think about all the field being uniform, relatively speaking, for example, in this area going from the plus charge to the minus charge. That was a roundabout way of explaining that, but I hope that makes sense. Does that make sense?
Yeah.
Okay. Cool. So let's, for example, take a look at the one I just drew in, right? If you take a look at this one right here, the blue surface, yeah? For the blue one, that's really category 2. Oh, we can do a color, yay, color. Okay, so is this, as Rhea would say, II? So we're really doing part II first. So this is part B. Oh, B, and we have part II there. Down here, part 2. So this is for R, smaller, little r, smaller for R. Okay, so that's kind of the blue one.
I have one question. The comparison to a capacitor makes sense to me, but I thought inside of a hollow conductor, like obviously there's another thing, but wouldn't the negative 2Q shell not matter because inside of a hollow conductor, electric field is 0?
So that's so you know, a little bit of knowledge is a dangerous thing, and you tricked yourself up there. You know something that's really good, but the thing you forgot is that that's only true if it is a metal material that has either no cavities, or if there are cavities, there is no charge in that cavity. So it violates the second aspect here. There is a cavity, and so it violates both. So it has a cavity and there's charge in there. Okay, so metal, a solid metal object in a static situation will have no electric field in it. That's true. But as soon as that metal object has a hole in it, a cavity inside it, then it could have electric field in it if there was a charge inside that. And that's the situation we have here. The solid metal stuff here, this area out here, it's very thin, right? But it has, of course, a non-zero thickness. Inside that actual metal, that solid metal, there is no electric field. But in between, there is electric field. Now, remember, it's really thin, this one right here.
Yeah.
So they don't even ask about it because they just say, but if they asked, like, if it was actually like a relevant thickness, but they just said thin, so zero thickness.
I know this doesn't really help answer the question that's at hand, but even if the inside, the inner cylinder weren't there, there could be and would be electric field inside?
Only if there's charge inside the cavity. So,
Okay.
so if we
No, that makes
remove
sense.
this thing, so we'd have to have a charge sitting in there, for example, just a floating electron or something. That would create electric field, but otherwise that wouldn't be the case. And it'll make sense as soon as we analyze the Gaussian surface. We've got this Gaussian surface, the blue one of radius r, right? This one right here, and we can draw that in. This is for part II. There we go. This is r. Okay, and we can say, okay, well, Gauss's law holds. I'm on screen? No, I'm not on screen. There we go. So the integral, surface integral, E dr, dA, this is a flux, is equal to Q enclosed divided by epsilon 0. Okay, Gauss's law?
Mm-hmm.
Okay, and we've chosen this thing in such a way that the electric field is constant. Cool, right? For symmetry purposes. So we can drop this integral and just say, oh, okay, well, this is just going to be E times A. And the A is of the blue cylinder. And Q enclosed is just the charge on the positive non-conducting cylinder thingamajigger, and that's just Q. And then we have epsilon 0. Now, the only thing we have left is to make sure that we get the area right, and then we're good. Good. So we're going to write that to the right, so I don't need to flip down the camera again. We can say E equals Q over epsilon naught, and then the area pops to the bottom, and of course that cylinder has a base of pi r squared. And then a length L for how much of the cylinder is being pierced by that flux, and we can box it and feel very good about our life.
So when the electric field is uniform, you can drop the integral sign.
Correct. So what you're doing there is you're summing up the flux over the entire area. But because E is constant over the entire area, you can basically pop this out front because it's just a number.
Okay.
And then, of course, the surface integral of dA, well, that's just A.
Yeah.
Okay, makes sense?
Makes sense.
Good. Okay, so let's take a look. So the same idea we just did would apply also to inside and outside. Inside's the trickiest, so we're just going to stay away from that for a minute. Color, yay, color. Let's do color. Okay, how about later on we're going to make that green. Green, and that's going to be kind of a surface like this. Yeah, so this is that one right there. Because it's visible that it's green. I'm not sure. Good enough. And then we're going to do one all the way on the outside, and that's going to be part III. It's going to be all the way around here. This is part 3. This is part 2. Oh, crap. Didn't mean to go blue. So this is part 2. And then in there, the green one is part 1. Maybe I'm having too much fun with the colors, but you can't stop me. There we go, part 1. There we go. So let's take a look at part 3. It's in purple. Nice thing there is that we have, of course, radius little r, and the same thing works out there. It's again constant, but this time we have a different charge. So the only thing that's changed is the amount of charge inside, right? So we had on the inside surface plus Q and the outside surface minus 2Q. Of course, that means the total charge inside the purple surface is Q plus minus 2Q, so that's minus Q. Everything's the same. Otherwise, and we can just rewrite that. E is equal to minus Q divided by epsilon naught pi r squared. Whoopsie, it's not really easy to read, is it? Pi r squared L. And we can box that in purple. There we go. And I scooched off the surface there. Okay, that's cute. Okay?
Mm-hmm.
Good, cool. And now let's look at the green area. For that, we're going to be inside the actual charge, and the charge is uniformly distributed. So we don't have all the charge in there. Okay, so that's the trick there. Again, the same equation applies in principle, but Q enclosed is going to be a little bit different.
Oh.
Okay, does it make sense? Does it make sense?
Yes.
Okay,
Because
so the same expression that we had here, really, right? But we got to make sure it's like Qn divided by epsilon naught pi r squared times L. But we got to make sure that how much charge is actually inside that. And of course, the charge inside that is going to be proportional to the fraction of the volume that we have inside that. And the fraction of the volume is lengthwise, we still have the same length, but we have only partially the area. Okay, so the fraction of volume we have there is going to be r squared, pi r squared divided by pi big R squared. That's the fraction of volume that's inside, which means Q times this. Technically, it would be an L, but we don't need that. We can cancel it out. Wow, I think I just confused you. Did I just confuse you?
A little bit.
Little bit.
Yeah.
All right.
Could you explain real quick one more time where the pi r squared over pi r squared is coming from? Because
Yeah. Hang on a second. I'm going to try and unconfusify you. We can do this. Okay. So we're looking at the charge inside the green surface there. Okay? So Qn is less than Q, right? Because not all of it is inside the green radius. That makes sense?
Yeah.
Okay. That's what they told us.
I get it.
The whole thing has plus Q. That makes sense so far? Okay. So the Q inside will be less than that. And specifically, it's going to be the fraction of Q, right? That is the ratio of the volume, the green volume, divided by the total, the black volume. That would be it. Oops, that'd be good. Oh, I can do colors. It's getting very schmeally here. So let's do this. So divided by the black volume. This is blue, actually. So the black. So the fraction inside this green cylinder is equal to the ratio of the volume of the green cylinder to the black cylinder times the total charge.
Okay.
Make sense? So in our case, we can plug the values in there. And we're in Greenland. Greenland's funny. Okay, so here we go. So write that over there. So Qn, I'm gonna come over here. Qn equals Q. I'll just write out the whole thing. The green volume would be pi r squared times L. And the black volume would be pi big R squared times L. Make sense? Okay. Yeah. And then, of course, that means, okay, the pi's cancel, the L's cancel, and it's just Q times the ratio of R squared, little r squared over big R squared. Cool.
Don't the little r squareds cancel?
Yeah, they do. Isn't that cool? I'm getting geeked out. Are you getting geeked out?
Okay. I am actually kind of.
That's kind of cool, right? So this cancels. So that's a constant electric field in there.
Ooh.
Crazy, man. Whack. As long as it's not zero, it's got to have zero electric field at the center, right? No, I'm hurting my head because we divided by it. We can't divide by it if it's zero. I think there's still zero electric field at the center, isn't there? Anyway, okay. So there we go. That's the electric field. Q in over, and then R squared pops to the bottom. And if we write that out, that means that E in that zone is equal to, top is just Q in, and on the bottom we've got epsilon naught pi L, and then we got an R squared on there as well. There we go.
Wait, no, isn't it just Q, not Q in, because we already...
Oh, yeah, yes, sorry. Yeah, correct. Plus Q, yeah. Plus Q over epsilon naught pi L R squared. And that's cool. And I'm hoping that's right. Let's see what they got for their solution. They got Q over pi R squared. Oh, that's just the same, sorry. Here we go. So part B1. Wait, what?
What?
We got a two, what's going on there? They got a different result, don't they?
Mm-hmm. Why do they have 2 pi r L for area?
Dum, 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 dum. Ah! Oh, we made a mistake on calculating the area. We calculate the volume, people, not the area. That's the
Oh.
yeah, that needs to be the surface area. I was just checking whether you're paying attention. Don't you love that line?
Favorite.
I thought a Gaussian surface was three-dimensional.
It is a three-dimensional, but the surface itself, we have here area, right? The area is in there. And with we, I mean me, I put this in, it's my fault. We put that in, that it's pi R squared L, but that's the volume of that cylinder, right? That's not correct.
Yeah, I understand that the volume isn't the area, but why isn't volume correct in a sense? Why doesn't it say like E with respect to volume?
Because the electric flux is proportional to the enclosed charge. So basically the idea is, and again, this is the conceptual idea. If you have charge like sends out electric field lines like pew, 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 right? And if you have more charge, it sends out more electric field lines. Pew, 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 pew. And if you have more of those electric field lines going out, they keep going out no matter what surface you put around that charge. All those, they'll shoot little electric field bullet holes into that surface. And that surface is basically catching all those bullet holes, and therefore E dA added up, the total flux is constant, because as those lines stretch out and go through different size surfaces, the total flux is still the same. I don't know if the pew, 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 pew helped.
Okay.
Jan is like, no, but I will just say yes. Okay. Okay, so we need to replace that. And on the picture, this will look good, and otherwise we'll look like fools. And by we, I mean me. So we're just going to correct this. So we have a purple marker somewhere. Geez, now you're losing. You got to drop it on the floor. Anyway, this might have to go a different color. Come on, people. Why did I go with purple? Here it is. Fun. Okay, so here's the area. Not pi r squared L, but indeed the surface, the side surface of this thing is 2 pi r L. Now that makes sense. 2 pi r is the circumference, and then times L. And then this over here also changes in the same way. So just pop the 2 down. There we go. Funny. Okay, so over here, same thing. So we have Qn r squared over big R squared, and down here, this changes, and now it does not cancel out that way. That did seem strange. I'm like, that did kind of geek me out. I'm like, that didn't make, and then I was pretending it made sense. Maybe, I'm not sure what I was doing. I was trying to make sense of it, but it didn't. So here we go. 2 pi r times L, and now one of the r's cancels. And here. So the nice thing, word of encouragement, they wouldn't ask you to do all this. That's ridiculous. You can't do that on that test. So they would ask you to describe how you would do it, right?
Okay.
And in that case, you'd be like just saying that the total flux through the cylindrical surface at radius r, right, is equal to the enclosed charge over epsilon naught or something like that, according to Gauss's law. Or just describing the process, right? So I would. What's that?
Sometimes when we do these Gauss's law problems, they integrate rho for the Q. Like why this time could we just do the fraction kind of thing? That's why sometimes you integrate.
Sometimes what happens is sometimes the rho is not constant.
Okay. Okay.
So because rho is constant, we don't have to worry about that.
Okay. So if rho is constant, we can just do the fraction.
Yeah. So let's take a look here, and this cancels. There's an r squared on the bottom, and there's one r on the top. And then there's also a 2 that we lost on the bottom. There's the r on top, and then there's a 2. There we go. So qr over 2 epsilon naught pi l r squared. And hopefully that matches up now. Yep, there it is. Yep, good. So now we're cooking with oil. Parts B1, B2, and B3. Ooh.
And what was the answer to 2?
Outside, yeah, it is a minus sign there. Minus Q over 2 pi epsilon. What's that again? 2 is now over here. It's, oh shit. Oh, I am on screen. Okay, good. It's Q over epsilon naught 2 pi r times L. It's hard to read. I will make it look a little bit thicker here by putting this 2. Okay, pi r L.
Yep.
There we go.
Thanks.
Cool. Okay. I'm going to take a picture. That's a pretty board. Okay, so picture. That's what I was going to do. Right? Physics C. Okay. There we go. I sent you the picture in the group. Now I can erase that. And just like leave the drawing maybe. If we need to come back to that. So here we go. Now, part C. Lost a little bit here. So that was page 1. Page 2. Okay, the cross-sectional views reproduced on the figure below sketch electric field lines in the regions. Oh, we already did that. Right?
We did it for ours.
Okay, so let's do it a little more carefully. So we've got this thing. We've got the big thing, and then we've got the small thing, and this has got kind of the non-conducting thingamajigger. And here we have out here negative 2Q, and this is plus Q, isn't this one? Good. And we already kind of drew that in, so it goes this way, right? We got that. So there we go. Okay. On the outside, the total charge is negative, right? So it points this direction. Okay. And the inside, we're positive, right?
Mm-hmm.
And it's proportional to R. Is that what we got? So it gets bigger as we get further out. Is that the result we got? How am I supposed to draw that?
It's probably just positive, like just going outwards.
Right, but those lines, you know, if I draw that this way, right? Like I would draw it this way maybe. But there's no electric field at the center. Make sense?
Oh, okay.
This is actually a bad drawing, and it looks like it's getting weaker as you get further out. So this is not a good way to represent this.
I agree that it isn't, but that's what they have, I think.
That's what they did too?
Yeah.
Yeah.
That's weak. We don't like it. Well, okay, fine. So actually it's zero electric field at the center, which makes sense, right? Because all the charge is symmetrical, right?
Mm-hmm.
So it should be zero at the center because the total, like all these basically would equally attract in every direction. Whoa, it's not even straight. There we go. So if you put it in, like Paul, remember Paul? Hey, what's up? I like Paul. Here's Paul. We put Paul at the center, right? Paul would be equally attracted by all the charges then, and all that would add up to zero, and would equally repelled by all these charges, so that would add up to zero electric field at the center.
Okay.
Yeah, so that drawing is really bad. So sometimes they do the sea of arrows thing. To kind of indicate more precisely what's going on. So maybe that would be a better way of doing this. Like do like little, like lots of arrows here. Have you seen seas of arrows pictures?
Yeah.
Yeah, so that would be kind of like, that makes maybe more sense to have like a sea of arrows like that, and then have it like get less like this. And then the idea would be at the center, there'd be none. That's a better way of representing. So in this case, actually electric field lines are not good to represent this. It's hard to picture them.
Mm-hmm.
Okay, good. So we are at 1C. Good. An electron is released from a point a distance 6r from the central axis of the cylinder. The following data are collected for the electron's acceleration as a function of the magnitude of the electric field E. Okay, makes sense. They should be related. Indicate below which quantities should be. Okay, that's interesting. All right. So somehow they magically measure E and A. Those for an electron. Those are obviously hard to measure. Okay, E and A. Both of those are hard to measure for an electron, I would think. This is meters per second squared. If you imagine having an electron somewhere, like here, tell me about the force it would experience. First of all, what direction would be the force?
Towards the center of the inner cylinder.
Yeah, that would be wrong.
I was gonna say to the right
It
because
would be kind of right away because it's a negative charge.
Oh, right.
Experience electric field in the opposite force opposite the direction of the electric field. So electric field is towards the center, and the force would be away. And of course, the magnitude of that force would be determined by multiplying
Electric field times Q.
Good. So it'd be Q times E. And for our case, it's EE, right? Shouldn't it be minus EE? Well, we already took care of the minus by pointing the direction. That make sense?
Okay. Mm-hmm.
Okay, so we have EE as the force. And of course, that is the only force acting. We're ignoring gravitational force. So EE is the force or net force. So sum of the forces. equals F equals this is the electric force, QE equals EE. And then, of course, the total force according to Newton is equal to
MA.
MA. Superb. Okay, now let's take a look. They have here E and A. So it looks like maybe we should use this as the X and use this as the Y. And I think that is good. If this is X and this is Y, right? Okay, this is asking us basically to solve this equation for Y, which is what?
Wait, what is X? What is Y? I got lost.
Okay, so the way they've got their table set up, right? They've got as the first variable E, so I'm going to assume that's the X variable.
Oh, then nice. You have
okay,
M over.
And it actually doesn't matter. So here's one of those calming moments. So for any of these graphs, if you do, YX, so in this case, AE, all good. But you can also flip them, that's fine. And you can do EA, it's going to be okay. The slope can still be related to whatever you're looking for. It would just be the inverse, okay? So you could still get there. So it doesn't matter if you screwed up, you plotted wrong, it's fine, you can still do it, okay? So in our case,
I understand that they're proportional, but wouldn't one have to plot QE, or in our case, EE?
That's our choice. No, they chose to plot E and A. That's what they said. And they said, the specific.
But I mean, on the graph.
Oh, so actually you could plot EE versus MA. That's okay.
Versus A.
You can't plot EE over E versus MA. That doesn't work actually.
No,
the reason it doesn't work is because we're assuming E and M are unknown. So you don't know E and you don't know M. Because the whole purpose of the activity is to find the ratio of the charge of an electron, E, to its mass. So we don't know E, we don't know M, you can't assume you know those, so you have to leave those in there, and actually the place to put them is in the slope. Okay, but you can plot E versus A, or
I assumed that we knew E.
A versus E or E versus A, either A versus E or E versus A, either one works. Okay?
Okie dokie.
Okie dokie. Okay, so we say E is equal to the charge of the electron to the mass of the electron times A. There we go. So in that case,
this is M over E.
It would, oh, I screwed it up, didn't I? Oh, I totally did it wrong. Wait, no, yeah, I did.
Yeah, we want A as.
Exactly, so this should be A and this should be E. Just checking if you're paying attention. Okay, so there we go. Good. And then we can do colors underneath because we like colors. We can say this is Y equals, I'm going to write slope. Same thing we had before because we've got here M. It's confusing for you guys generally. So this is X. This is Y. And then the slope is E over M. So the slope of that line will be E over M. So if we look at this, when they graph it, they do graph it, don't they? Yep, there we go. Here's the graph. Let's assume we did that. Whoop. The slope of that line should be the ratio of the charge of the electron to its mass. And looking at this thing, 20 over 3.2 about. Okay, so we find a slope of 20, and then in the y direction, this is times 10 to the oh, interesting. No, they're actually plotting, this is for E versus A. Interesting. Okay, so this should be then 20 on the bottom. Okay, so their plot is the other way around. That would be 20 times 10 to the 3. And then over here, for this one would be 3.2 times 10 to the 15. 2 times 10 to the 15. And this should, in the end, because it's the charge of electron to the mass of the electron, coulombs per kilogram would be the units in that. This means E divided by ME equals this. Okay. And that would be about equal to 1.6 times 15, 12, 11, 10 to the 11 coulombs per kilogram. Right. That's close enough, I'd say. Did that make sense, or was that confusing?
No, that made sense.
Made sense? Okay, good. Okay, cool. Let's see if there's anything left we need to do. We got problem D, and somehow my whole stack of papers got out of whack. So we just get D. Are we done with the problem?
Yeah.
Okay, cool.
Yay.
Yay, that's pretty good. And again, if they're asking you this on Monday, they will, I could see them doing this problem. It's okay. As long as instead of asking you to define the specific, like 3 Gaussians and all that stuff with the manipulation, that seems a little excessive. They probably would ask you to describe how to do it, and they would give you the actual graph and then ask you to find it off that, like I did that on the practice E&M one where I gave you the graph and gave you the slope actually. I'm okay with that, and then asking you to manipulate that to get the E/M ratio.
Okay. So they could still ask us to derive like we did for part A, do you think? Or just explain that?
I think part A, so I think they would reserve the right to do this. And as long as it's only that kind of thing where it's like R, L, Q, you know what I mean? Like our final answer wasn't like so wacky that you'd be like sitting there for like 15 minutes trying to figure out how to write it down, right?
Yeah.
Because it was a reasonable, it just had QRL, maybe a pi in it or something like that. You can write that down. It's okay. You can type it in, and I think you're still fine. They will make sure that you type it down. I do think that this is not justify heavy enough for, or explain, because I think they're going to have more explain and justify than they have here, because of the nature of the beast.
Okay.
But in principle, I mean, this is good physics. You got to know this stuff. So I'm glad we talked about it either way. Cool. So that brings us to the end of the problem. We only have about 5 minutes left. So I think we're going to end here. But what's your situation? Did you guys want to do this again tomorrow, or what's your sketch?
I would, if you guys are okay with that.
Yeah, just generally like the practicing for sure.
Okay.
Yeah.
All right. Well, good. Then I'll schedule again for tomorrow. As this is a good time, except for we're crashing right into Sammy's Kaffee und Kuchen side. I don't know if just what our plans are tomorrow.
I don't care if you guys want to do a different time. That'd be fine with me too. I don't know.
Yeah, neither do I.
Okay. Well, you're very, very, very inputful there. So 3 o'clock seems fine. So maybe we just stick with it then, because you don't seem to be tending any other direction. Okay.
Yeah.
Well, let's plan on a meeting again tomorrow at 3 p.m. And I can stop this now, because it seems silly to even have that discussion on.